So this is a paradigm. We're going to talk about it in the next few lectures. And today, mostly want to talk about this part. And we probably won't even finish, but I want to talk about this part. How do we take classical code and convert it to equivalent quantum code? And in some sense, you kind of thought about this a little bit already. Let's say on maybe homework 1, where you kind of have these little programming tasks in quantum, where you were like, if you just let me write classical code, this would be real easy. I would know what to do. And that's sort of the situation we're a little bit in, where you easily imagine you have some classical code that does some tasks. You're like, no, now I need quantum code to do the same task. But actually, before we talk at all about how can we figure out the quantum code, we're actually going to spend the entire time talking about what should it even mean to have equivalent quantum code. That's literally all we're going to talk about today. What should it even mean to have equivalent quantum code? So, okay, so we imagine we have some classical code, which I'll call CCode for brevity. And it has n input bits, and it spits back to you m bits. And, let's assume it's deterministic. So it computes a function, right? It computes a Boolean function. Let's also imagine, you've proven that it runs in a finite amount of time. So it always halts. It doesn't loop forever. So it really always gives an output. No nonsense like that. So it computes a Boolean function, which I'll write like this using, mathy notation. Okay, the input is all possible n-bit strings, and all the outputs are possible m-bit strings. And I really, for the purposes of today's discussion, I really want to make a careful distinction between the function that's being computed and the code that's implementing that function. So you should really think of the function as the spec, the definition for what the code is supposed to do. It really tells you exactly for every possible input string, what is the correct desired output string. And you should think of this, CCode, as some actual programming language code in Python or C or whatever that implements this spec. Okay? So I kind of came to it backwards. I first imagined it had some code, and then we wrote down or we imagined writing down okay, what is the exact set of all output pairs, the function that it's computing. But maybe you should have in mind for this discussion the reverse, where somebody gives you a spec, I want you to compute this function, and you might have different ways of making code for it. Okay? So let me give you a bunch of examples, and you might be I don't need this many examples, but let me give you this bunch of examples so we have them to talk about. So here's one you may remember well. N and M are both 2, and you think of the bit strings as representing numbers mod 4, written in base 2. And F is, increment mod 4. Okay, it's F of X is X plus 1 mod 4. Okay, you possibly remember this one well from homework 1, question 1. Okay, that's the spec for a really simple function. And if I was okay, write me a tiny computer function that does that, you would be no problem. I guess you toggle the last bit, and you also toggle the first bit if the last bit was 1 or whatever. Okay, here's another example. N is 16, M is 8. The bit strings kind of represent numbers, 8-bit numbers. Well, okay, so let me say the input bit strings represent 2 8-bit numbers, and the output is their sum. Well, mod 2 to the 8, I guess. Okay, so there's it's kind of f of x, y equals x plus y, but you delete the higher the carry bit. Okay, that's a basic function. It's a classic function that's implemented on your somewhere on a chip on your laptop, probably with this being like 64 instead of 8. So it's used a lot. Again, here's some more examples. N is like 1 million, and M is 256, and F is like SHA-256. This is like some popular cryptographic hash function that takes in, well, strings of any length, but let's say 1 million bits, and always outputs 256-bit strings, and it does it in some funky way. Okay, let's do another one. Maybe N is 1024, just because that's a popular length for big numbers. M is 1, and F outputs 1 if and only if the input number, thinking of this as a number in base 2, is a prime number. This is also like a popular task in computing. I give you like some big number with many digits. Tell me if it's a prime or not. And it's like maybe you remember from like 251 and stuff, it's pretty common to like think a lot about the case where M equals 1. That's where like the output is 1 bit. It's like a yes or no kind of question. Okay, I'm still going to keep going. Let's do like N is 3, M is 2, and F just truncates off the last bit. That's an easy function to write code for. You just like, f of x1, x2, x3, return x1, x2. And maybe the last one, just like for classic 251 sake, f outputs 3 input bits, 1 output bit. F outputs 1 if the input string is a palindrome. Okay, if it reads the same forward and backwards. Okay, so there's many different tasks that you might want to write a computer program for. And for any of these like functions f, you could write several different blocks of code called CCode, which implement these functions. Okay, and I bring them all up so that we can start talking about this question. How should it even mean to convert classical code doing something to an equivalent quantum code that does the same thing? Because almost all of these are not even reversible, right? Actually, one of them is reversible. I know you know which one. It's the first one, happens to be reversible by some luck or weirdness. This one happens to have the property that, like, the spec, F, it's like a bijection. It's like a permutation on all the strings. It's reversible. All the other ones, they don't even have the input and output, like, length the same. There's no chance they can be reversible. So, for example, it leads to a problem like, these are all classical functions. So in principle, like, you might say, like, I don't even need like the Hadamard instruction or anything. Like, maybe I can just get all these things done with like toggle and if then toggle and if A and B then toggle. Well, no, you can't, because all those instructions are reversible. You can only make reversible subroutines out of them. But like 99% of the time in life, the code you care about is not reversible. So we have to like decide to change what it means for like a quantum program to like compute these functions. So that's what we will discuss now. Okay, so there's like one basically official definition that we'll eventually come to where it's like, here's by default what we always mean when we talk about quantum code that computes SHA-256, or quantum code that adds two numbers, or quantum code that checks for a palindrome. There's eventually going to be like a default definition for like what that means. But before I give you that, I'll give you some special cases that are easier maybe to think about, and sometimes it'll be important to use them. So yeah, we're trying to answer the question in general, like, what should QCode do? Not even like how should we get to do it, but like just what is it supposed to do? So let's do special case 1, which rarely comes up, but occasionally comes up. And we will actually need the special case later in the course, so like let's discuss it. This is the case where like n equals m and f happens to be reversible. Very rare. But like, it does sometimes come up. For example, this like, increment mod 4 function or increment mod 8 or anything, I mean, you could draw, well, actually, let me not put these symbols here. You could draw like sort of the truth table or like the paths diagram for what increment mod 4 does. And you're like, oh, check it out. Like, by a miracle, this is reversible. Like, you know, it's a bijection. So in this case, you can say to yourself, here, we could hope that QCode literally does F. I mean, but with qubits. Because we know that like all possible, you know, quantum, you know, qubit manipulation operations, they're unitary. They have the unitary property. And in particular, the only ones that have this classical form that have the unitary property are like the reversible ones, the undoable ones. But like, hey, I told you we're in this special case where this F happens to be reversible. So this like can, in principle, be programmed by a quantum computer. So in that case, we may frequently say like, okay, that's the definition of what QCode ought to do. It ought to just literally do F, except with qubits instead of bits. Now, one thing you have to think about is that's your definition of what QCode ought to do, but it's maybe not obvious how to get it to actually do that. It may be not obvious how to get it to actually do that, even if you're staring at classical code that does it. Because the classical code doesn't just have to use reversible instructions. Like, the classical code isn't, like, required to just use, like, if, then, toggle and stuff. It can do whatever you want. Like, I could have, like, on homework 1, written you, like, a short Python program that did increment mod 3. And I'd be like, you know, get quantum code that does exactly this. And you would probably be, like, find that problem equally challenging, even though you have the classical code. Because the classical code is not using reversible instructions. It's doing it in like a normal way. And the task there is figure out how to do this with only the classical reversible instructions. And that was a little tricky, if I recall. So all I'm saying here is that like even if you like have code that does a reversible function f, classical code, it's maybe not obvious how to get quantum code that does that function f. But that's what we are going to require. And I'm telling you now, it's actually not that complicated. So we will do it. By the end of next lecture, you will know how to take classical code for computing a function that happens to be reversible. Actually, I guess you also need the classical code for the undo of f. And with those two pieces of classical code, there's a mechanical way to just transform them into quantum code that literally does f. But we'll get to that. But this is just to say this is what we're going to choose to do, or to try to do. Okay, so that's a special case where it's pretty clear what the spec for the quantum code should be, or there's a reasonable choice for it, and that's the choice that we'll take. Now this, as I said, this special case is pretty rare. You know, out of all those examples on the board over there, only one of them had it. So now let's talk about another special case which is pretty common. Special case that's quite common. And that's just the case that m is 1. Okay, this is a case where the code, or let's even say the function, only outputs 1 bit. So it returns 1 bit, returns true or false. You know, this is like a decision problem in like 251 language, or a language, and it's a pretty general case. So there's a few examples of that here. I guess like this one has 1 output bit. This one has 1 output bit. So maybe we'll focus on the palindrome one just for laughs. So for example, you know, we have this like n equals 3 palindromes function. And let me draw like the sort of truth table for it. Like this path diagram, but it's also like a truth table. 1, 0, 0, 1, 0, 1. 1, 1, 0, 1, 1, 1. And like, okay, that's all possible inputs. There's only 2 possible outputs, 0 and 1. Okay, and palindromes looks like this. Okay, hopefully I get this right. All the non-palindromes go to 0. All the palindromes go to whatever I said. All the palindromes go to 1. All the non-palindromes go to 0. So this is kind of like the definition for palindromes function. It's like the spec. You know, if I was like, write some classical code that implements this function, you'd be like, no problem. Actually, it's pretty much one statement. But, you know, I only chose n equals 3 so I could draw it on the board. If n was 1,000, you would still be like, no problem. I can check if it's a palindrome. But, yeah, so this is, maybe I have 3 bits here. I'll call them B1, B2, B3. But maybe it's palindromes. OK, so you look at this, and you're like, well, this is most definitely not reversible. I mean, the number of input bits and the number of output bits is not even the same. So it's literally impossible for quantum code to do this, because quantum code is always undoable. It's always reversible. So this is not possible. So now it's like we have a design decision. We're like, well, we still want to have a notion of quantum code computing palindromes, or any function like this. Like, what can we do? We need to like invent like a unitary transformation, like a valid paths diagram that does somehow correspond to palindromes. So here it is. This is like a candidate spec for QCode. Okay. We're going to be like, OK, we want to make basically if palindromes, then minus. I will explain what I mean. We're going to call it like, we're going to try to make a subroutine that we will name if, well, let me write it in sort of the general case. If B1, B2, Bn, then minus. And you're like, I don't know what that means. Well, I will tell you right now exactly what I mean by this. Defined as follows. Okay, so now I'm giving you like the definition of a candidate quantum transformation, a candidate unitary transformation. I'll describe it in words. So to describe it, you know, like when I was describing like what Hadamard does or what clockwise does, I just tell you how it's supposed to operate on all the basic states. So if the input basic state is, let's say, B1, B2, dot, 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 Bn. The output is supposed to be 2 cases. If the correct output value is 0, then don't do anything. Just return the input state. On the other hand, else, if it equals 1, like if the correct answer for B1 through Bn, according to f, is 1, then you pretty much return this basic state, but you put amplitude minus 1 on it. Amplitude negative 1 on this basic state. So let's check a few things. First of all, this is like sensible. Like this is a valid quantum state. It has all 1 of its amplitude on this particular basic state. This is also a valid quantum state. It sort of also has all 1 of its amplitude on this basic state, except it has amplitude minus 1. But that's allowed. We just need sum of squares of amplitudes to be 1, and minus 1 squared is also 1. So this is a legit quantum state for every possible input basic state. Now, you should say, like, well, be that as it may, I don't know for sure that this is a possible quantum transformation because, like, it should be unitary. So, like, is this unitary? Well, think about that. Is this unitary? Does it have the unitary property? Well, let me start drawing the candidate paths diagram for what this supposedly is doing. So for the candidate paths diagram, I have to now say these are qubits. So I'll put the funny brackets. And it's going to be a quantum transformation. So like the outputs, these are the possible outputs. I won't draw all of them. Okay, and apparently, okay, so for 0, 0, 0, it is a palindrome. So the output of f is 1, like, yes, palindrome. So we do change the amplitude to -1. So what I'm saying is like this. 0, 0, 0 goes to 0, 0, 0, but with amplitude -1. And 0, 0, 1 is not a palindrome, so f of that is 0, so we don't do anything. Well, we have amplitude +1 on this, so +1. 0, 1, 0 is a palindrome, therefore supposed to get amplitude -1. This is not a palindrome, so amplitude +1. Not a palindrome, so amplitude +1. Okay, there's 3 more, but I won't draw them. So this is a funny paths diagram, but okay, it's a paths diagram. So now let me ask, does this have the unitary property? It's not a classical reversible instruction, so that's not helping you, but it's still pretty straightforward. So, well, you kind of know the answer. I wouldn't ask in this leading way. Yes, it has the unitary property. Why does it have the unitary property? Do you want to say? Exactly. So let's repeat that. In general, like, before you do this hypothetical instruction, like, you could have, like, I don't know, like, A amplitude here, and B amplitude here, and C amplitude here, and, like, whatever, G? H amplitude here. And then what would the outcoming amplitudes be? Well, you know, the outcoming amplitudes would have, like, in this case, like, minus A amplitude, plus B amplitude, plus minus C amplitude, plus D amplitude, ... So the outcoming amplitudes would again be like A, B, C, D, blah, 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 except maybe with minus signs. But what would the final sum of squares of amplitudes be? It would still be A squared plus B squared plus C squared plus D squared plus et cetera. And therefore, if this was like a valid state coming in where the sum of the squares of the amplitudes was 1, then indeed the sum of the squares of the amplitudes coming out will also be 1. So we just checked that this candidate hypothetical instruction is a unitary transformation. Therefore, by what I told you earlier, it can in principle be done in like our physical world, and like you can, I also promised you that like every such unitary transformation can be programmed using our basic instructions. So we don't know as of this moment how to like program this transformation for palindromes out of our current instructions, but I'm here to tell you it can be done. So again, maybe in like the next lecture, we'll see how to actually write quantum instructions that implement this transformation. But now at least we were like, okay, this is like a valid spec that we could require. Okay, maybe I've convinced you that like, yes, we'll be able to write some quantum code that like does this transformation. And maybe even if n is like 1,000, you know, you can like give it an input string, it'll basically return the input string back to you, but with like a sign, plus or minus, depending on whether that input string is a palindrome or not. Then you could be like, hey, will this be good for anything? Let me remind myself like what was going on. He said we're going to like get into the uniform superposition where we have like equal amplitude on all the inputs. It's kind of like 1, 1, 1, 1, 1, 1, 1, 1, 1. And then we're going to do this code. So then we're going to have like amplitudes still like 1, 1, 1, 1, 1, but plus or minus ones, like minus 1, plus 1, minus 1, plus 1. And be like, that's cool. Like somehow the amplitudes learned the palindrome status of all possible 2 to the n input strings. Like that is so cool. But like then what? For example, maybe as you were suggesting, like if we just said extract all now, what would happen? Something very sucky would happen. All the squared amplitudes are 1. They're all equal. So if you like did a normalized state, like they'd all be plus or minus 1 over square root of 2 to the n, but they'd all be equal up to signs. So the squared amplitudes would all be the same. So the program would just output a random string. And so like you got nothing. It like the output did not even reflect the fact that you were talking about palindromes. Like that got washed away when you did extract all. So nothing good happened. And in some sense, yeah, that's like typical status. Like quantum computing, like what is it good for? Like nothing. But we didn't do the whole paradigm. The whole paradigm was like first get here, then do Hadamard all for some reason. And that's like does like a Fourier transform on this like data, and then extract all. And if you do that, something kind of interesting could happen. And like, yeah, like in the next 4 lectures, we'll kind of exactly address this. Like, if you have some starting kind of data that maybe like encodes the palindromness of like all possible strings with the signs, and then you do this Hadamard transform, and then you do extract all, does that tell you something interesting about palindromes? Well, we'll see.